All right, we'll start it. Okay, any other homework questions?
Yeah, good.
Which one?
3, 4, and 5.
All right.
I have on 3 and 4. I wasn't sure what it was asking. Oh no, on 2 and 3. 2 and 3, I wasn't saying. I didn't know what that question was even asking me to do.
What does it mean to give a direct?
Epsilon dash and verification.
What's an epsilon?
It's just saying prove it directly, no using theorems that we've already proved. So it's just saying use the limit of convergence directly. The epsilon n, it's saying basically make sure you use the Archimedean principle somewhere in there. But we'll go over it. So when it says, what is it? Prove that the first one at the limit of 1 over the square root of n, did I see that right? Square root of n, not square root of 2, is equal to 0.
It says the limit as n approaches infinity.
Yeah, so so far, anytime we've been taking limits, so we had this discussion before and I said I wasn't going to do it, but yeah, we'll write that way. And we'll re-go over what we said. The limit as n approaches infinity. So far, when we've been taking limits of sequences, we've been always doing it as n approaches infinity, as n gets bigger and bigger. And so I've always just done the limit there because we haven't had to talk about other types of limits yet. So every time I put this on the board, it's been shorthand for this. We've never been taking any other type of limit. Make sense?
So what are examples of a different limit that you would do?
Right, that's why I didn't bother because we haven't been talking about the limits as a function approaches a point yet. So we'll get there. Okay. So let's see what we want here. So they're saying use an epsilon m proof. They just mean make sure you use the Archimedean property. How am I going to start every limit proof? 1. What's my first line always going to be?
Epsilon.
Yeah.
Plus.
Let epsilon be some positive number. Right? Now ultimately, what am I trying to do? Let's get some scratch work on the side. I'm trying to get 1 over the square root of n minus 0 less than epsilon for all n greater than or equal to some big N. So I need to find some big N that makes this statement true. Once I find some big N that makes this statement true from that big N onwards, we've proven it. Make sense? So some scratch work. Let's see. I need 1 over the square root of n to be less than epsilon. Well, minus 0. But this is just the same thing as 1 over the square root of n. Right?
Yeah. Wait. Is that only for n is greater?
Since n's always a natural number, it's always a positive number.
N is always natural number, that's right.
Right? So this is always going to be a positive number. So this will definitely be less than or equal to 1 over the square root of big N, if we just make that. If n is always greater than or equal to big N, a bigger denominator makes a smaller number overall, right? So I need this to be less than epsilon. So I need to find a big N that makes it less than epsilon. Or I need 1 over n to be less than epsilon squared. Right? And there's my big leap. 2. By Archimedean principle, there exists n in the natural numbers such that 1 over n is less than epsilon squared. Right? Epsilon is just a positive number, so epsilon squared is just a positive number. I'm guaranteed by the Archimedean principle that for any positive number I pick, I can always find a natural number n such that 1 over n is smaller than that number, whatever it is. Right? So then 1 over the square root of n minus 0 is less than or equal to 1 over the square root of big N is less than epsilon for all n starting at that index. And we're done. Right? I found an index, big N, such that this distance is less than epsilon from that index onwards. You remember the picture in your head of what we're doing? This is just some sequence. We're going along in the sequence and we're finding the point in the sequence where from that point onwards, the sequence is always within epsilon of what you're saying it converges to, in this case 0. Don't lose track of big picture what we're talking about. So, make sense? Pretty straightforward. So, now looking at 3.
Sorry, are you missing any on this?
Nope. So now 3 is almost the exact same thing, right?
It basically is. It's just
Right, so you want me to do 3 or should we move on?
Can we do 3?
We sure can. Alright, 3 is just another limit. Just hold this so I can see it. So we want to show that the limit of 2 over the square root of n plus 1 over n plus 3 is equal to what?
3.
3, right? You should be able to see that right out the door. For really big numbers n, this goes to 0, this goes to 0, we should just be left with a 3, right? Same thing as always, 1, let epsilon be some number greater than 0. Scratch work over here. So I'm trying to show 2 over the square root of n plus 1 over n plus 3 minus 3. I'm trying to get this thing less than epsilon for all n starting at some index. If I show that this is true for all n starting at some index, we're done. Let's simplify this. This is the exact same as 2 over the square root of n plus 1 over n, right? 3's go out. Okay. Let's get a common denominator here, put those things together. So this is equal to 2n plus the square root of n all over n times the square root of n. Did I do that right?
yeah.
And since everything's positive numbers, we're still just positive, so I'll get rid of my absolute value while I'm at it. Good? Now we can see that we can cancel square root of n out of the top and the bottom. So we have 2 square roots of n plus 1 over n. If I take square root of n out of this, I'm left with 2 square roots of n. If I take square root of n out of this, I'm left with 1. If I take square root of n out of this, I'm left with n. Good on the algebra there?
Yeah.
Okay. Let's see. This is going to be less than or equal to, if I get rid of that 1, I made it smaller, not bigger. So, here's what we'll do. This is less than or equal to, I'm trying to make this thing as simple as I can, but as I'm making it simpler, I can only make the number bigger. I can't ever make it smaller. Make sense? Because as I make it bigger and bigger, if I still make sure, no matter how big I make it, if I still keep it less than epsilon, we're good. Because if whatever I make, however big I make it, if I make whatever that thing is less than epsilon, I'll have for sure made this less than epsilon, I'll for sure have made this less than epsilon. So as we're doing this simplification, make sure you're always just making it bigger, not smaller. So, to make this bigger, I'm going to multiply. I'm going to replace this 1 with the square root of n. Right? Square root of n is always greater than or equal to 1. Square root of 1, 1. Square root of 2, bigger than 1. Square root of 3, even bigger. Square root of 4, even bigger. Right? So I can rewrite this as 2 square root of n plus square root of n over n. And we just made it bigger, not smaller. Right? Once again, canceling out square root of n out of the top and the bottom, I'm left with 3 over the square root of n. You see that? Square root of n out of here leaves 2, square root of n out of here leaves 1, add them together leaves 3, square root of n out of here leaves square root of n.
Right.
You see that? Alright? Okay, so now I just need to make this less than epsilon.
How can you just say that though?
Well, when is this less than epsilon? This is less than epsilon when 1 over n is less than epsilon squared over 9.
Yeah.
Right? So to get from here to here, multiply both sides by 9, which gives me 9 over n is less than epsilon squared, and then square root it. Gives me 3 over the square root of n is less than epsilon. Good?
No. I'm confused.
Okay, maybe I skipped one step here that I shouldn't have done. Okay, so this is true. This is going to be less than or equal to 3 over the square root of big N for all n greater than or equal to big N. So if a big N is a smaller natural number than little n, this inequality is true. I make the denominator bigger, it makes the number smaller. So since little n is greater than or equal to big N, this inequality is true, right?
Mm-hmm.
Now by the Archimedean property, I know, we'll just come over and start right over here. By Archimedean property, there exists some natural number n such that 1 over that natural number is less than any positive number I want. Right? So I can put any positive number here I want. What positive number am I going to choose? I'm going to choose epsilon squared over 9. So when I choose epsilon squared over 9, then 1 over n less than epsilon squared over 9 gives us, multiply both sides by 9, gives us 9 over n less than epsilon squared. Take the square root of both sides, gives us 3 over the square root of big N is less than epsilon. Right?
Yeah.
Now I know, for all n greater than or equal to n, this inequality is true. So then, 2 over the square root of n plus 1 over n plus 3 minus 3 is less than or equal to 3 over the square root of n for all n, which is less than epsilon, for all little n greater than or equal to big N. And obviously I'm referencing scratch work over there, so I don't have to rewrite it in the proof.
I have a question.
Go ahead.
So in my proof, it was similar to yours, except for I showed that the limit of each of those three numbers, or sequences, I guess, I showed what their limit was and then added those limits together. Does that work?
That is.
Well, the problem says.
That works in terms of proving it. That doesn't work in terms of you're going around how the problem wanted you to do it. The problem wanted you to show that this converges to this using the definition of a limit directly, not referencing theorems. So I would never dock you for doing a proof that way, but that's not specifically what the problem said to do.
So I would get docked on that problem then.
If I bothered writing in there, make sure you prove it this way, I doubt I'd do that.
Oh, okay.
But if I did say that specifically, then yes, you would get docked for that, but
Also, instead of showing that the limit of 3 over the square root of n goes to 0, then I would show something like 3 times the limit of 1 over the square root of n is equal to the same thing. Like I would factor out the 3.
yep, that's perfectly fine. Because we proved theorems that allow you to do that. But once again, that's always behind the scenes using our direct method, which is what we did here. So this is just direct proof. Any other questions on the proof? Any other homework problems you want me to go over?
Yes.
Alright, which one?
Number 4.
Number 4.
I mostly just didn't know which sequence it was talking about. And then I didn't know what B and C were asking anyways.
So, gonna have to get that one out of the book, so I just have answers written. We didn't know what sequence it was talking about. This is calculus. What number was it?
Number 4?
Number 4. For sequence AN, defined in example 2.3. So I'll scroll up to example 2.3.
It would be n over n plus 1, right? No? Is that right?
No. Example 2.3. It's listing out all the rational numbers. So remember, I don't know what class it was in, but you were asking me what's the function that maps all the natural numbers to all the rationals, and I told you it's a somewhat convoluted function. That's exactly what we're going to be going over here now.
Oh, nice.
So AN is I guess we can write it this way. AN is equal to, the first thing in there is 1 over 1, and then you get 1 over 2, 2 over 2. I think that's how we're doing it. Yeah. And then you get 1 over 3, 2 over 3, 3 over 3, 1 over 4, 2 over 4, 3 over 4, 4 over 4, 1 over 5, and I think you get the pattern. Right? Now, below they tell you how to get the sequence. I wrote exactly how we needed. The sequence's first 11 terms are displayed above, more formally defined as follows. Since for any natural number, so you're saying, remember that the sum from k equals 1 to n of k is just equal to n times n plus 1 over 2. So that's what he's saying right there. So since for any natural number j, 1 plus 2 plus 3 all the way up to j is equal to j times j plus 1 over 2, for an index n written as that, I don't know why we need that since part, but so let's see. So we're saying, here's your index n. N is equal to j over j plus 1 no, j times j plus 1 over 2. Oops. So n is equal to j times j plus 1 over 2 plus k, where k has to be between 1 and j plus 1. K 1 less than or equal to k less than or equal to j plus 1. So make sure you write your index this way. Then a sub n is going to equal k over j plus 1. All right, so let's see this in action.
Well, what's the definition between n equals, or I'm sorry, what's the difference between n equals that and then a n equals that?
So they're saying, here's for an index n, here's how you figure out what k and j are, and then here's how you figure out what the nth term is. So we'll just do it for some of these. So pick one of those, I don't care which one.
The fourth one.
So the fourth index, so 1, 2, 3, 4. So we're going to pick n has to be 4. We'll do scratch work over here. So we're picking n equal to 4. Okay, so I need to express 4 as this right here plus k, where k is in between 1 and 5. Oh, no, 1 is whatever j plus 1 is. So let's see.
That's what got confusing.
So,
Find out what J is.
What is k?
where k
Is, no.
j times j plus 1 over 2. Let me think. So let's just think what we know it should be. So you said the fourth term. So we know that our k should come out to 1. So this should be 3. In order for this to be 3, j is equal to 2. 2 times 2 plus 1 over 2 plus 1. Right?
Yeah, but how did you do that?
That doesn't work.
So then a of n should equal, my j was 2, so 2 plus 1 is 3, and in the numerator I should have whatever my k was, which is 1.
So your k is always moved here.
Yeah, whatever the k is should turn out to be your numerator here, and whatever j plus 1 is, you're just looking for the j plus 1 and k that add up to your n,
Is there,
where this condition is met.
is there only one combination of j and k that makes that true?
That makes this true? There better be, or we're in trouble. So let's look for the 11th term real quick and see how that turns out for us. So 11, and let's just play with this one more. So let's do 11 equal to, and we can start throwing around some guesses at what j could be. So randomly throw out, I don't know, 3. So if we tried that, what would we have? We'd have 3 times 3 plus 1 over 2. What's this equal to? 6. So 6, and I have to plus 5. Wait a second. Is 5 in between 1 and 4? No, so I picked too small of a number for j. So let's try, j has to be 4. What do we get? So if we make j 4, we get 4 times 4 plus 1. What does that give me? 10. 10 plus 1, does that satisfy this?
Yeah.
Yeah, it does. Okay, there we go. So it should be 1 over 5. So a of 11 better equal 1 over 5.
Okay, that makes
So let's do another one. Let's find the 15th term. The 15th term, let's see if using 4 still works. So what do we got? We got this is equal to 10, so we still need 5, right? So, is 5 in between 1 and 5? Yep. So it works. So this one, our 15th term, a sub 15, better be 5 over 5. Which it would be if we continued this out, right?
Yeah.
And so now we can find any term we want. What's the, I don't know, 32nd term going to be? So what do we want for J? Pick a guess. Should we try something like 6?
Yeah.
6, what do we get? 21. So that was definitely not going to work. We're way too far away. What about when we try 7? What's 7 going to give us?
Mm-hmm.
28.
Yeah.
What were you doing?
I was.
Oh, you multiplied it first?
Yeah.
One of these is always going to be even. So
Yeah.
cancel out with your 2, then multiply. So that's going to equal 28. Why do I have 15 here? I don't know why I have 15 there. We're looking for the 32nd. So we want 32 is equal to 28 plus 4. Ah, does that satisfy this condition? Yes, it does. Okay. So our 32nd term then is going to be 4 over 8. Right? Here's my numerator. Here's my denominator.
Okay.
So let's see. So part A was asking what's the 10th term going to be, the 20th term going to be, and the 30th term going to be. Now you know how to find those terms. B wants us to do the reverse. So B says, when are we going to get 2 8s in this sequence? What index is going to give us 2 8s? So we know our k is going to be 2. We know that this right here is going to be, this term is going to be 7 plus 1, which makes this 7, and this 2. This is a term that's going to give us 2 8s. And what is that? 30. So a sub 30 is going to equal 2 8s, which obviously, since we know 32, a sub 30 is 2 8s, a sub 31 is 3 8s, a sub 32 is 4 8s,
I
and it
thought
continues.
what we were looking for was a sub n equals 1/4, not 2 8s.
2 8s.
2 8s is the second 1/4 in the sequence.
Oh, is that what it says? I'm just looking at my paper. I didn't read the problem.
Index n for which a n equals 1/4.
Okay, yeah, the second time that we get 1/4. So we got 1/4 at 1/4, then we're going to get it here, then we're going to get it at 3/12, and we're going to get it at 4/16, etc. What's next?
Show that an equals 1/2 for that n that you choose there.
Geez, that's a big section. Yeah, so we won't worry about B anymore. I think you can do that. So C, for J, an odd natural number, set n equal to that and show that an is equal to 1/2. Okay. So what are we trying to do? We'll write this out as a little proof. Proof times j plus 1 over 2. J times j plus 1 over 2 plus j plus 1 over 2?
J plus 1 over 2.
Thank you. J plus 1 over 2. Then a sub n is equal to 1/2. So let's just prove it. 1. Let j be odd. What does it mean for j to be odd? 2. Then there exists some a in z such that j is equal to 2a plus 1. That's the definition of odd. So now plug 2a plus 1 in for j on n. So then what does n equal? Then n is equal to a plus 1 times a plus 2 all over 2.
2a.
Thank you. Then n is equal to 2a plus 1 times 2a plus 2 over 2 plus 2a plus 2 over 2, right?
Okay.
Actually,
Where are we
the
going?
n doesn't matter. We want to just go straight to saying that an is equal to 1/2. So whatever this simplifies to, we don't really care, because we know that this is our denominator and this is our numerator, right? So let me go straight to this instead. So then a sub n is equal to, well, k over j plus 1 is equal to, what's k? K is, why does it matter that j is odd? See if you can help me see why it matters if j is odd, because I'm getting a sub n is equal to k over j plus 1. K in this case is going to be,
Because if j is even, then j plus 1 is odd, and it can't be 1 over 2.
well, I'll show you the issue I'm seeing. J plus 1 over 2, there's k, all over j plus 1 is equal to 1/2 times j plus 1 over j plus 1 is equal to 1/2. So I'm getting an. If n can be expressed this way for any j, then I'm getting an is equal to 1/2. So why do we need j to be odd?
Because if j is odd, then that is the special case for n, right? Because usually n equals plus k.
Right, so I just did a straight substitution.
Oh.
So if k is j plus 1 over 2, I don't see why it matters if j is even or odd. So let's try and come up with an even j that works for this. I don't know, 2. So let's say if j were 2, then we've got 2 over 3 over 2 plus, oh, because k needs to be an integer. We didn't really specify that over here, but k has to be an integer. K is not an integer unless j is even, or j is odd.
Why does it have to be an integer?
That's just part of the example. So express n where it's equal to j times j plus 1 over 2 plus k, where j and k are integers that satisfy this.
And that's that. And you have
That's how you get n.
k has to be an integer because you want the numerator to only be an integer, right?
Well, we're just saying express n, which is an integer, as this plus this, where j and k are integers.
Okay.
We're not saying any real number that satisfies this, put that for n, because n has to be an integer.
Right.
Alright, so that's why it had to be. J has to be odd so that this is an integer, and then this all works out. So a n is always equal to 1/2 when j is odd.
Okay.
So I'm not sure what I did in my work there. Okay. So there. Did you have more questions?
When the book says to show something, does that mean prove it like you did?
Mm-hmm.
Okay, then how do we prove that a n does not converge?
Is that part D?
Yeah.
Show that a n does not converge. Okay. Probably proof by contradiction. So we'll just write it right here. Obviously, the a n that we're talking about is still just this thing. So proof. Does not converge. 1. Assume, by way of contradiction, that it converges, and we'll call whatever it converges to A. So saying it converges is the same thing as saying the limit exists. If the limit exists, we can name it. I may call the limit of whatever the sequence is A. Right? So, 2, then there must exist some index in the natural numbers such that the absolute value of an minus a is less than epsilon. Didn't pick a epsilon. Oh, I just picked a number. It's less than 1/2 for all n greater than or equal to n. Right? So if this sequence converges, then this gets arbitrarily close to A the further we go. And so for sure, there has to come a point in the sequence where this distance is always less than 1/2 from that point onwards.
Yeah.
Make sense? Okay?
Wait. Why is it less than 1/2?
I can choose any positive number I want. Since I know that an converges to A,
Oh.
then for any positive number I choose, there has to come a point in the sequence where this distance is less than the positive number I choose from some point onwards.
Right.
So 3, then there, how do I want to say it? Cannot exist two indexes. That's a better way to say it. Then a sub n1 equal to 1/2 or 1, doesn't matter, and a sub n2 equal to 1 can't both be true for n1 and n2 greater than or equal to that big N. So, should have probably started with the big idea here. The big idea here is that in this sequence I may have infinitely many 1s. Doesn't matter where I am in the sequence, if I keep going far enough, I'm going to come across another 1. Similarly, I'm always going to come across 1/2.
Mm-hmm.
So that's the whole big idea of choosing this. I can't get this arbitrarily close to this number. I can't have the distance, I can't have the range my sequence covers from a certain point on less than 1/2, because I know I'm always going to be able to find two numbers whose distance is 1/2. So that's what I'm saying here. I can't have 1/2s keep on showing up and 1s keep on showing up after this index if both these numbers are supposed to be in 1/2 of some number. I should have chosen 1/4. Just realized.
Why?
So let's draw a picture real quick. Here's A. Here's a minus 1/4. Here's a plus 1/4. It's impossible for me to have both 1 and 1/2 in there. Right? Because even if A is right smack in the middle of them, A equal to 3/4. Let's see, 3/4 plus 1/4 puts us right here, and then A minus 1/4 puts us right down here. So if I only look at numbers in between, I'm guaranteed not to have both 1 and -1, or 1 and 1/2. So if A is right smack in the middle of them, then I don't have either of them. If I shift it up a little so I include 1, then I don't have 1/2. If I shift it down a little so I have 1/2, I don't include 1. So I can't have both of them. I can't have both 1 and 1/2 within 1/4 of A for any number A.
Okay, but how are 1 and 1/2 involved in the convergence of A and minus A?
So big picture thinking is, I know that this thing doesn't converge because I know it has infinitely many 1s and it has infinitely many 1/2s. So whatever it does, it eventually reaches 1 and 1/2, 1 and 1/2. So it can't be getting closer and closer to one number. Because no matter how far I go, I'll eventually get another 1, and I'll eventually get another 1/2. Does that make sense? It's kind of like an alternating sequence. So if we were just looking at 1, 1/2, 1, 1/2, 1, 1/2, we know that doesn't converge because it doesn't get closer and closer to anything. Right? So if we were graphing it, 1/2, 1, if we're looking at a sequence that just goes 1/2, 1, 1/2, 1, 1/2, 1, 1/2, 1, we know it doesn't converge. It doesn't get closer and closer to a number.
Okay, but how do we know that this sequence does do that?
That has infinitely many 1s and 1/2s.
Or are we?
This is the sequence we're talking about.
Okay.
Yeah, sorry, should have specified that better. Because this is
That
part
makes sense.
4, it's the same problem.
Right.
Okay, yeah. So yeah, this is going to have infinitely many 1s and 1/2s. And so it's ultimately going to have this jumping around. It's just going to be more spread out with some terms in between. Okay. Good. Now we're all on the same page. Okay. So, if A converges to A, then A cannot be within 1/4 of both 1/2 and 1 from this index onwards. Right? You good with that? Okay.
Actually, isn't that exactly what we're proving in number 5? But there's infinitely many 1s or 1/2s, I can't remember.
On 5? For the sequence AN, define in example 2.3, and any rational number x in the interval 0 to 1, show there are infinitely many indices n, such that AN equals x. It's a very similar idea.
I don't know, I'm just saying, how can you say that you know that there's a 1/2 and a 1?
I didn't yet. All I said is, if this is true, then for sure I cannot have a sub n1 equal 1/2 and a sub n2 equal 1, where those are indices after n, because they're not both within 1/4 of any number. That's all I've said so far. So I didn't say anything about there is going to be infinitely many numbers, infinitely many 1s and 1/2s. So I need to show that that's going to be the case. So 4. Let j equal 2n plus 1. Let's remember our sequence that we're talking about, so that our n's and j's make sense. So n is equal to j times j plus 1 over 2 plus k, where 1 is less than or equal to k is less than or equal to j plus 1, or just less than j plus 1? I think it's less than. So that's our n, and then what was a sub n? A sub n was equal to k over j plus 1, right?
You have
Oh, less than or equal. Yeah, that makes sense, because we can get 5 over 5.
Yeah.
Okay, perfect. So I'm saying if j takes this form, watch what happens. So let j equal 2n plus 1 and k equal n plus 1. And maybe I'll say then, so that you see it's a calculation. Then n1 equal to, what do we get when we plug this in for j and this in for k? We get
2n plus 1
2 big N plus 1 times
2n plus
2n plus 2 all over 2 plus n plus 1. And all that really matters is this is going to be greater than or equal to n. Right? This is a positive number. This is n plus 1. So n sub 1 is greater than or equal to n. When I have j and k defined this way, comma, and a sub n1 is going to be equal to then k over j plus 1, which is, maybe we'll write it out, k over j plus 1, which is equal to n plus 1 over 2n plus 2, which is equal to 1/2. Okay, so I found an index, big N sub 1, where a at that index is equal to 1/2. Now I'm going to do the same thing for 1. Right? 5. Let j equal to n plus 1 and k equal to n plus 2. Then n sub 2 equal to 2n plus 1 times 2n plus 2 all over 2 plus 2n plus 2 is greater than or equal to big N, comma, and a sub n sub 2 is then going to equal, same thing, k over j plus 1, which is equal to 2n plus 2 over 2n plus 2 is equal to 1. Contradiction. 6, therefore, doesn't converge. Right? You follow the logic there? No? Here's the heart of it. So this is the line that you need to understand. If an gets within 1/4 of a from some index onwards, then if an is always within 1/4 of a from some index onwards, then an cannot be both 1/2 and 1 after that index. So if I can find an n sub 1 and an n sub 2, such that a sub n1 is equal to 1/2 and a sub n2 is equal to 1, then if I can find two indices greater than big N that make this true, then an does not converge. Right? So the whole problem from here on out is just find two indices, n1 and n2, such that an at 1, an1 is equal to 1/2 and an2 is equal to 1. Once I do that, I'm done. So I just found some. Right?
How did you find them?
Look at this.
That makes sense.
I just want this to be 1/2. So pick an n and so pick something for n and j that make that true. Where did I put the mark card writing? So when I want this to be 1/2, where can I make that happen? Well, I can do that at 2n plus 2 for j and n plus 1 for k.
That just popped into
So, well, notice that this gives me 1/2. And I need to make sure that however I get the 1/2, the corresponding index is also bigger than n. So I'm constructing it in terms of this big N to make sure that its index is greater than or equal to big N. So, when I let j equal 2n plus 1 and k equal n plus 1, then the index is going to be this thing, which is greater than big N. So I just basically need my k. If I just pick a k that's bigger than big N, in this case big N plus 1, then we're good. So make my numerator big N plus 1, right? And then find the denominator that makes that 1/2.
Oh, okay. Except right there, you had j equals 2n plus 1.
J equal to 2n plus 1. So j plus 1 is 2n plus 2. Because remember,
Oh.
the nth term a sub n is j plus 1.
Right.
So 2n plus 2. So I just need to find some index that gave me 1/2. There were tons I could have used. I just found one. Similarly, I need to find a place to make this 1. Notice that this is only going to be 1 when k is equal to j plus 1.
Right.
So 2n plus 2 sure works.
Could you have chosen different numbers then?
Yeah. There's infinitely many. I just have to find one. So that's the heart of the proof. If you understand this line, you understand the gist of it, and then it's just finding an index after that. That's for sure bigger than big N. Here's one that for sure is. Here's one that for sure is. This index gives me 1/2. This index gives me 1.
And proving that 1/2 and 1 are in there, it doesn't converge.
Yeah, so what I'm saying is, if it converges, then the distance, starting from some index onwards, an has to be within 1/4 of a. And it is impossible for both 1 and 1/2 to be within 1/4 of a. There is no number that's within 1/4 of 1/2 and 1. Right? 3/4 is right smack in the middle of them. And 3/4 is barely not within 1/4 of 1/2, and it's barely not within 1/4 of 1. Because it's exactly 1/4 away. So it's not less than a fourth. Right? So since these two numbers can't both be within 1/4 of a, then if I show that an gives me both these numbers after this index, then it can't converge. The intuition for why this doesn't converge is just that we're always going to eventually get 1, then 1/2, 1, then 1/2, 1, then 1/2. So it can't be getting closer and closer to something. That would have been how you explained it in a regular calculus class. Observe that you get infinitely many ones, observe that you get infinitely many 1/2, therefore it doesn't converge.
Can we do 5 as well?
Sure. 5. Oh, that's 4, 4. Where's my 5? Therefore, AN does not converge. And then I have 6. I didn't do 5.
Weren't you just looking at 5?
I did 4, and then I did 6. So I skipped 5. Oops. That means I probably didn't need to assign you guys 5. And accidentally just wrote it. For a sequence AN, define example 2.3, and any rational number x in the interval 0, 1, show that there are infinitely many indices n such that AN is equal to x. Let's think about that. So I want AN equal to any rational number. So just do like some thinking work over here. So a rational number is always going to be of the form A over B, where those are integers. So I want A over B equal to J plus 1 over, K over J plus 1. K, I wrote it wrong again. K over J plus 1. So for any AB you pick, I should always be able to find an N that makes that work infinitely many times. So let's write it out in particular instances and see if we can find a pattern. So let's start it out for 1/2. How can I always get 1/2? That's going to be when we have J plus 1 and J plus 1 over 2. How am I going to argue that there's infinitely many of those? If I know that A sub n is equal to 1/2, I know that K is equal to J plus 1 over 2. So I know that N is equal to J times J plus 1 over 2 plus J plus 1 over 2. Let's try another one. AN equal to 1/3. That gives me that K is equal to J plus 1 over 3, right? Which gives me N is equal to J times J plus 1 over 2 plus J plus 1 over 3. So let's think about one more time. AN equal to A over B. Then K is going to equal Did I do K right up here? j plus 1 over 3. I don't know. I'll have to think about that one. I don't want to spend a bunch of time trying to figure it out right now. So skip that one. Any other homework problems?
You're saying we don't have to do that one? Or just do it later?
Yeah, you don't have to do that one. And then I'll try and get the solution figured out. Because, yeah, I skipped it. Weird. All right, any other ones? Okay, so we're ready to continue with the material finally. Okay, so let's remember where we left off. So first off, let's remember the comparison lemma. And that was the limit of, how do I want to mark this? So I'll just say that we did it as a proof. We proved that if the limit of an is equal to a, and if there exists c greater than 0, thank you, such that c greater than 0 and n sub 1 in n, such that, keep losing my spot, b sub n minus b, such that b sub n minus b is less than or equal to c times a sub n minus a for all n greater than or equal to n sub 1, comma, then the limit of bn is equal to b. So we did that proof last time. We did the proof that page. We did the proof that if the limit of an is equal to a and the limit of bn is equal to b, then the limit of an plus bn is equal to a plus b. We did the proof that I don't want to skip any of those things. We proved that if the limit of an is equal to a, comma, then for alpha in R, comma, the limit of alpha times an is just equal to alpha times a. In other words, if we have a constant in there, we can just factor the constant out. If you have any questions about these as we write them, let me know.
Just trying to remember what they are all saying.
Yeah. The next one was proof if the limit of an is 0, then the limit of an times bn is equal to 0. What do I have that there? That. And then for a homework problem, you guys were supposed to prove that the limit of an equal to a, excuse me, the limit of an equal to a is logically equivalent to the limit of an minus a equals 0. Then the product proof that the limit of an times bn is equal to a times b, where a and b are the limits of an and bn individually. Well, maybe I'll write it this way. Is equal to the limit of an times the limit of bn, where those exist. And I think that's what we ended with last time, right? So now we're going to continue with, we're going to do a proof that if an converges to a, I think I'm going to write in terms of bn, so that when we reference it in our proof, the variables match up. So proof that the limit of bn equal to b implies that there exists some index n such that absolute value of b over 2 is less than, or bn is greater than that. Yeah, that's a better way to write it. Such that the absolute value of bn is greater than the absolute value of b over 2 for all n greater than or equal to that index. And then we're going to prove that the limit of 1 over bn is 1 over b. Limit of 1 over bn is equal to 1 over b, where b is the limit of this. Obviously with b not equal to 0, otherwise it doesn't work. And then we're going to do our proof that the limit of an over bn is equal to a over b. And then we're going to prove linearity. We're going to prove that the limit, finally our last one will be, well, our second to last one, we'll do one after all these. Proof that the limit of alpha times an plus beta times bn is equal to alpha times the limit of an plus beta times the limit of bn. That's an easy one, but just having one proof to reference for that is always nice. And then we'll do our proof that we briefly talked about for polynomials last time. Proving that the limit of a polynomial is the same thing as the polynomial of the limit. So, any questions on the ones that we've done so far? Otherwise, we're going to start here. Good to just go?
I think so.
All right. So we're going to do proof that and write out exactly what we're going to assume. If the limit of Bn is equal to B, where B is not equal to 0, comma, then there exists n in n. Marker's dying. Is this one I was using before? Not great, but. If the limit of Bn equals B, where B is not equal to 0, then there exists n and n such that the absolute value of Bn is greater than the absolute value of B over 2 for all n greater than or equal to n. Sorry. All right, 1. So let's start it. I think I'm going to start with let Bn such that the limit of Bn is equal to B with B not equal to 0. So assume that Bn is some sequence that converges to B where B is some non-zero number. So 2, then there exists some index n such that Bn minus B is less than the absolute value of B over 2 for all n greater than or equal to big N, right? That's what it means for this to converge. If Bn converges to B, then for any positive number we pick, notice B is not 0, so absolute value of B is a positive number. Positive number divided by 2 is a positive number. So for any positive number we pick, then this is true from that index onwards. Do we need to take a break, Levi?
Yeah, I need to get up and walk around, I think.
All right. We'll take a break. We'll kind of recap this. I'll just write out the proof. You guys can take a break, and then that way I can at least write it nice, so you guys aren't just staring at me while.
Sorry.
No, it's all good. You need a break, you need a break. That's how life goes sometimes. So I'll rewrite this out. It's not all squished.
Did the time change?
I don't think so.
It doesn't change till November.
November?
Yeah, I don't remember which day.
Maybe I'll go get some water. You ready to continue?
Yeah, I'm all cold now, so I can stay awake.
Am I not yelling enough? Ah, I was about to erase that. Okay, let's continue. So, let's recap what we were proving. We're proving if Bn converges to B, where B is not equal to 0, then I can find some index n such that from that index onwards, Bn is greater than half, the absolute value of Bn is greater than the absolute value of half of what it converges to. It's kind of intuitive. The absolute value of Bn then should get arbitrarily close to the absolute value of B, and so there should come a point where it gets greater than the absolute value of B halves, right? That's all we're proving. Okay, so let's have a quick. So let Bn be some sequence such that its limit is B where B is not equal to 0. So we've got some sequence Bn converges to B. All we know is that B is not 0. So since it converges to B, then we know that there exists some index called big N, such that from that index onwards, this is true for any positive number we pick. Right? Pick a positive number, this is a positive number. Then this is less than this from some index onwards. That's what it means to converge. If Bn converges to B, then for any positive number you pick, I can find an index n such that from that index onwards, this is true.
Okay.
This is typically we use an epsilon symbol to represent that, right? Everyone with me? Sleepy Joe? Observe that Bn and B have the same sign when this is true. So from n greater than or equal to n. If you can't see that right out the door, just draw a little picture for you. One of two things, B is either a positive number or B is a negative number. So B is either over here or over here. In either case, we know that Bn is within half of the absolute value of B. So here's B. So the absolute value of B over 2 is this distance. So Bn has to be within this distance of B. So Bn is either going to be, either way, Bn is going to be on the same side of the number line as B. If B is positive, Bn can't be negative. If B is negative, Bn can't be positive. It has to be in this interval. You see that? So if B is positive, Bn has to be within this interval, which can't reach past 0. If B is negative, Bn has to be in this interval, which can't reach past 0. So B and Bn have the same sign. They're either both positive or both negative, whenever this is true. If Bn is within that distance of B, those two have the same sign.
And we're just, are we doing anything to prove that, or just say, hey, look at this?
No, we're just saying notice that.
Okay.
We don't want to take time to expand this into a big inequality showing that it's impossible for one to have one sign and one to have the other sign, so it leads to contradiction where you get it's both greater than and less than 0 or something like that. So, they both have the same sign. That's all I'm trying to note here. Probably obvious, but just in case. Okay, so let's handle the two cases. Let's handle the case where they're positive, and then we'll handle the case where they're negative. Oh, I didn't specify it here. This is true for all n greater than or equal to n. I just want to rewrite it this way. Any problem with rewriting this inequality like this? Okay, so then I'm just going to use this half of the inequality for the positive case, this half of the inequality for the negative case, and then that will handle both. So if Bn is greater than or equal to 0, then taking this half of the inequality, that's all I've written right here. Right? Now since Bn is greater than 0, B is greater than 0, what's the absolute value of B?
Just B.
Just B, since B is positive. So this can be rewritten this way.
Wait.
Since the absolute value of B is just B.
How do you know that Bn is greater than 0?
If Bn is greater than 0, we're handling both cases.
Right.
Okay. So if they're positive, then the absolute value of B is just B, right? All I did is replace absolute value of B with B.
Oh.
Yeah. Okay. And then add B to both halves of the inequality. Add B to both sides of the inequality, not both halves of the inequality. I was thinking halves.
Okay.
So negative B halves plus B is B halves. Bn minus B plus B is just Bn. And then finally, since B is positive, B and absolute value of B, same thing. Since Bn is positive, Bn and absolute value of Bn, same thing. So we get this inequality, which is what we were trying to get. So if Bn and B are positive, this is true. Now we're going to show it's true in the case that they're negative. Therefore, it's always true. We good with the positive case? Okay. Negative case now. So if Bn is less than 0, then this is just the right-hand side of this inequality. So take the right hand side of this inequality. It's right there. Good? Now, since b is less than 0, the absolute value of b is negative b. The absolute value of negative 3 is equal to negative 3. Yeah, the absolute value of negative 3 is 3, the negative of what was in here. So if b is a negative number, then its absolute value is b with the negative in front. To cancel it out, make it positive.
Oh,
Because b is negative, yes. So both bn and b are negative. They're less than 0. So this gets rewritten this way. And then, going from here to here, just add b to both sides. Good? And then, bn is the same thing as negative absolute value of bn, since it's a negative number. And b is the same thing as negative absolute value of b. Negative 3 is the same thing as negative absolute value of negative 3.
Okay. So you're saying right there where negative b, clear over. Clear over. That's over. This way. Other way. Negative b over 2.
Which one?
The one that actually has a negative sign.
Negative absolute value of b
Not
over
that
2.
one. This one right here. Right here.
Negative b over 2.
It literally
Right in
does
the
it.
middle of your
Right in the middle of my line.
Are you saying that that's
Right here,
positive?
okay.
You're saying that's positive.
Negative b over 2 is a positive number.
That is so confusing.
I know, that's
And
what I
you're
warned you
saying
with.
b over 2
absolute
is
value.
negative?
Yeah, so b over 2 is negative. So if b is negative 3, then this is 3/2, and this is negative 3/2. And now we're back to 3/2.
Okay.
Oh no, this is still negative
No, we're
3/2,
negative,
sorry.
yeah.
Yeah, we didn't change it. So going from here to here, same exact thing. Right? Okay. Oh, and then one more step. So now I'm going to multiply both sides by -1, which flips the inequality. So we still got that in the negative case. So in either case, it works. Therefore, we're done. Therefore, bn is greater than b/2 over 2 for all n greater than or equal to some index n. So we found the index that makes this true from that index onwards. Right? Okay. So that's this proof. Any questions on it before I erase it? All right. Forever hold your peace.
I hope the camera can see it well.
So do I. I hope the camera's still going. Okay. Now we were going to do, so we did this one, now we're doing this one. This proof, by the way, was just a lemma to help with this proof. The author combined them both into one massive proof. I thought it was better to break them out. So now we're going to prove that the limit of bn, no, 1 over bn, right? The limit of 1 over bn is equal to 1 over b. Well, let's specify that a little bit better. Because we need to say what the b is. So if the limit of bn is equal to b is not equal to 0, comma, then the limit of 1 over bn is equal to 1 over b. That's really what we're proving.
That's for any sequence b, right?
For any sequence bn that converges to b that's not 0, then 1 over that sequence converges to 1 over b. Pretty intuitive. So let's prove it. Let bn be a sequence such that the limit of bn is equal to b is not equal to 0. So we know since Bn is a sequence that converges to b is not equal to 0, then we know that there is some index to, then there exists some index n such that the absolute value of Bn is greater than or equal, or just greater than absolute value of b over 2 for all n greater than or equal to n. So that's just using this real quick. Okay, now remember what we're trying to prove. Where are we ultimately trying to get? We'll do some scratch work down in the bottom over here. We're trying to get that 1 over Bn minus 1 over b converges. We're trying to get that this converges to this, right? And so this is going to be equal to, do some scratch work real quick. This is going to be b minus bn over b times bn. Getting a common denominator, right? Which is going to be equal to 1 over b times bn times b minus bn, right? And then I'm going to use the fact, let me rewrite this one more way. This is 1 over the absolute value of b times 1 over the absolute value of bn times b minus bn. And then I may use that fact up there that I know that from some index onwards, the absolute value of bn is greater than b over 2. Another way that we could write this, if we write it as, what does that tell me about 1 over the absolute value of bn? I know this is less than 2 over absolute value of b, right? This inequality can be rewritten this way. Right? So,
Wait, how? Oh, yeah.
okay. So, this whole mess then, sorry, lots of scratch work over here, I know is going to be less than or equal to, when I replace my 1 over bn with that thing, I could have only made it bigger, is going to be less than or equal to 2 over the absolute value of b squared, absolute value of b twice, times b minus bn. So I'm going to get that this is less than or equal to some positive number times something that I know converges from some index onwards, and then I'm going to use a comparison lemma.
Oh. Okay.
So that's big picture how all this is going to come together. Okay? So, 3. Then, the absolute value of 1 over bn minus 1 over b is equal to the absolute value of b minus bn all over b times bn is equal to factor out the denominator, so we're going to get 1 over absolute value of b times absolute value of bn times b minus bn is then going to be less than or equal to 2 over the absolute value of b squared times b minus bn for all n greater than or equal to big N. Whatever the big N is up here that made that true. Right? Okay. tie it all together so that we can see the comparison line at one go. Then 1 over bn minus 1 over b is less than or equal to 2 over absolute value of b squared times b minus bn for all n greater than or equal to n. 5, therefore, the limit of 1 over bn is equal to 1 over b by comparison limit, but I guess we didn't name it up there, so using this proof.
Line 4 doesn't exactly fit that proof, because doesn't bn and b have to be switched around in that equation?
Doesn't bn and b have to be?
Doesn't have to
Oh,
be the
yeah.
sequence minus the limit.
Oh, you're right. So 1 over bn minus b can be rewritten as, I see what you're saying. So let's do some scratch work real quick. So this is the right order here, right? Bn minus b. Oh, you're saying here's where we have the wrong thing.
Yeah.
Okay, so which is equal to 2 over, 2 over the absolute value of b squared times, rewrite it in a different order, how should we say it? Some new sequence, negative bn. Let's see, we can rewrite it like that, right?
Yes.
Or we can rewrite it like this.
Okay.
So, I don't know which way is easier to say it. If we want to say that negative bn converges to negative b, we could, that's going to obviously be true. Since bn converges to b, then a constant times this is going to be a constant times that.
Oh, right.
So that's one way that you could justify that if you want. The constant being negative 1, right? So I know that this converges to this, therefore comparison limit makes it hold. Good? No?
I don't see that.
So we'll just show this real quick. Bn minus b, that's not quite what we're saying. We're saying that the limit of bn equal to b is logically equivalent to the limit of negative bn is equal to negative b.
Oh, okay.
And how do we say that? Because we know that the limit of a constant is a constant times the limit. So negative 1 times this is just negative 1 times, gives us negative 1 times this. So that gets us from here to here. Same thing all from here to here. Multiply by negative 1 gets us from here to here. So we're just using this twice. Right?
Yeah.
Okay, good catch. All right, any other questions about the proof? All right, on to the next one. So, let's see, where is the next one? Oh, the product. So now the product is going to be a breeze, or not the product, the quotient. So, quotient says if the limit of an is equal to a and the limit of bn is equal then the limit of a n over bn is equal to a over b. Make sense what we're proving? Let an and bn be sequences such that the limit of an is equal to a, and the limit of bn is equal to b is not equal to 0. 2. Then the limit of an over bn is equal to the limit of an times 1 over bn is equal to the limit of an times the limit of 1 over bn is equal to a times 1 over b is equal to a over b. And we're done. I think that was pretty straightforward. Any questions there? Okay. Then, what do we have? Okay, linearity property. This one's also very straightforward. Proof. If the limit of an is equal to a, the limit of bn is equal to b, and alpha and beta are real numbers, comma, then the limit of alpha times a plus beta times b times a and bn is equal to alpha times a plus beta times b.
I thought we already proved this.
We've proven all the pieces of it. This is just a proof that's telling us that we can do this all in one go,
Okay.
so that if I were making you sit there and reference proofs for every line that you used, you now had one spot that you could go and just use that. So, in other words, this gives us that you can multiply by constants and add limits all in one go. And obviously, that's what we're going to do.
Why is it called the linearity property?
So it's called the linearity property because something is linear if I can apply an operation to it. If I can do a times x plus b times y, where x and y are the variables and a and b are just constants, if that ends up equaling a times f of x plus b times f of y, then we call it linear. Things that preserve this linearity we're very interested in. So this is a fact we use a lot in linear algebra. So operations that are linear. So f isn't necessarily a function, it's just, well, I guess you could always think about it in terms of a function, but it's just some operation.
Is that what we're trying to prove? Or is
Yeah, this is exactly what we're proving. So we're proving when you apply some operation to some real number.
no, but look at what that says down there. That's not what you wrote.
Oh, so this was just in general. This had nothing to do with what was up there. So
Not that.
I was just talking about the linearity property in general. So we're saying a constant times a thing that's varying plus a constant times a thing that's varying. These always have to be real numbers. Is the same thing as a real number times applying it to just the x plus that real number times just applying it to the y.
Right, I got that part.
So we're saying that the limit of alpha times an plus beta times bn is equal to alpha times the limit of an. Maybe rewrite it like this.
See, that was my point.
Okay, yeah. So we can rewrite this as the limit of an, and it shows up better with how I have it written here,
Yeah.
plus beta times the limit of bn. So limits are one of these things that are a linear operation.
Does linearity have anything to do with what we know in Algebra 2, 1, and
Does it have anything to do? Trying to think if, well, no, that's not a good way to say that. I think introducing it in vector spaces is the most intuitive place to show you what linearity is.
Okay.
Because then you're not just dealing with real numbers. So, well, I guess you aren't here either. You're dealing with sequences. I don't have a good way of just giving you intuition for what the naming is on that. Okay, so here's what we're proving. Let's do it real quick. Let AN be n such that the limit of AN is equal to A and the limit of BN is equal to B, comma, and to let alpha, beta be real numbers. Okay. 2. Then we know that the limit of alpha times AN plus beta times BN is just going to be, so the limit of a sum is the sum of the limits. So the limit of alpha times AN plus the limit of beta times Bn, and then we know that the limit of a constant times a sequence is just a constant times the limit of the sequence. So alpha times A, and the same thing, beta times B, and we're done. Right? Okay. So finally now, we get to our polynomial proof. So now we need to prove that, you remember what a polynomial is? So we need to prove that the limit of the sequence you get plugging a sequence into a polynomial is equal to just the polynomial at the limit of the sequence. So
could you go over again, like exactly what you define the polynomial to be?
yeah.
Last week?
So definition. Well, I won't bother writing a polynomial is blah blah blah. We'll just say it's a polynomial. P of x is a polynomial if you can write it as the sum from k equals 0 to n. This is an nth degree polynomial. An nth degree polynomial, and we can have it for any n that we want, is equal to, at x is equal to a sub 0 times x, or a sub k, times x to the k, where a sub k is just some real number.
Where a sub k is just a real number.
Yep. So an nth degree polynomial is just expand this sum out, where the a sub 0, a sub 1, a sub 2, whatever they are just real numbers, and it's x to some natural number power. So a third degree polynomial, for example, p sub 3 of x is equal to a sub 0 times x to the 0 plus a sub 1 times x to the 1 plus a sub 2 times x to the 2 plus a sub 3 times x to the 3, where a0, a1, a2, and a3 are any real numbers you want. Pick any real numbers you want, it's still a third degree polynomial. So a particular third degree polynomial would be something like pi x to the 0. X to the 0 is always just 1. So pi x to the 0 plus e times x to the 1 plus square root of 2x squared minus 397x cubed. Okay, there's an example of a polynomial. In this case, it's a third degree polynomial.
So A is a 1 degree.
Yeah, so a sub 0 is just some real number. In this case, pi. A sub 1 is just some real number. In this case, e. A sub 2 is just some real number. In this case, square root of 2. A sub 3 is just some real number. In this case, negative 397. Good? So, that's what we mean by an nth degree polynomial. So I need to show, and I'm going to do an inductive proof, that for any degree of polynomial, this property holds. So I'm going to do a proof that P sub, I don't know, I'll do n. If the limit of a n is equal to a, then the limit of p of a n,
Are we even
I'm
talking
using
about
two
limits?
n's. We'll put a k there. Then a kth degree polynomial, the limit when we plug in a n, is just equal to p sub k at a for all k in n. This is true for any polynomial you pick. We'll just leave it like that to represent any polynomial. Or maybe I can specify. Then the limit of p of n is equal to p of a for any polynomial p of x. Okay, that's what we're going to prove. Now remember that when you plug a sequence into a polynomial, it gives you a sequence. Right? So p of a sequence is still just a sequence. So we're saying if an converges to a, then the limit of p of an is still a sequence that converges, and what does it converge to? P of a. That's what we're going to prove. And we're going to prove it inductively. So, let blah, 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 blah. Let an such that the limit of an is equal to a. Okay, 2, base case. So our base case, I guess we could do our base case. We can do both k equals 0, k equals 1 is our base case, doesn't matter. We'll just do base case, we'll just start it at 1. So base case, I can't use n since I'm using a sub n in my sequence. So what should I use for my inductive variable? T, just picking something. So we'll start out base case t equal 1. Then the limit of p sub 1 of a n is just equal to the limit of what does a first degree polynomial look like? Ooh, shoot, we also use a's a lot here. I'm going to use b's for my sequence. That way you don't get confused when I use a's for my real numbers. You okay with that?
Why are you thinking?
Yeah. While she's gone, let's just pause for a second and I'll do it cleaned up. So let's restart, let's clean it up. I want to use a's up here. I want to use a's the way I do in polynomials like this, so I don't want to also use it for my sequence. That's what I mean. So if Bn is a sequence that converges to B, then the limit, and we won't even do Bn, let's use a different variable down here. Let me keep my n's and my k's. So what should we use? Bj. That's typically what we use for some integer. So if b sub j is some sequence that converges to b, then the limit of p sub n sub j is just equal to p sub n of b for all n in the naturals. Okay, that will help me use my n's in my case I want. With me so far?
Can you help me understand what that is really saying?
If b sub j is some sequence that converges to b,
Okay.
then
So
for
shouldn't that,
any nth degree polynomial,
okay,
the limit of the sequence that you get when you plug in b sub j into the polynomial is equal to what you would get if you just plugged a b into the polynomial
oh, okay,
for any nth degree polynomial you want.
okay.
What does it look like to plug a sequence into a polynomial?
Okay, so let's pick some simple sequence and simple polynomial. So we'll pick the sequence just 1 over j, since we're using j now instead of n. So here's some sequence in terms of j, 1 over j. And let's pick some, what degree polynomial? And we'll say p of 2. Some second degree polynomial is going to look something like this. A sub 0 plus a sub 1 times x plus a sub 2 times x squared, right? So when I plug this sequence, 1 over j, into this polynomial, what do I get? So p sub 2 of 1 over j then is equal to this sequence. A sub 0 plus a sub 1 times 1 over j plus a sub 2 times 1 over j.
And 1 over
Squared. Sorry. In general, p of any sequence you want, a sub, I don't want to use a sub n, we'll use b sub n. P of b sub n, if it's a second degree polynomial, is always going to look like a sub 0 plus a sub 1 times b sub n plus a sub 2 times b sub n squared.
And in the middle row, we're treating 1 over j as a sequence.
As the actual sequence. So what's 1 over j? It's 1, 1/2, 1/3, 1/4, 1/5,
I'm
etc.
just getting confused because we're treating it as if it was like an actual number, like by itself instead of sequence.
No, it's a sequence. I just didn't want to keep using n's over and over again. So this is just so I don't have to write 1 over n, because I guess I could have down here.
Could you
It's just up
ever
here.
simplify one of those?
Simplify one of these.
I don't think you could you? And if you did, what would you?
You can't write it
plug
simpler than that.
Okay. But what would you write the bn as? Just bn,
Just being.
the sequence of bn.
And then if you want
Even if
to
the end was
explicitly
defined.
write it, you have like a table.
Oh, no. So let's do a very, very concrete example real quick.
Okay.
So let's use the very concrete sequence 1 over n, and the very concrete polynomial p of x is equal to 2 plus 3x minus x squared. Okay? So then, what is p of 1 over n? It's going to be a sequence. What's the first term in the sequence? Well, when we plug 1 in for n, what do we get? 1. So 2 plus 3 minus 1 is 4. 4 is the first term in p of 1 over n. Now plug 2 in. 2 gives us 1/2. 2 plus 3/2, what is that? 7/2. Minus 1/4 is 27/4, I think. Whatever.
27 boards. How did you do that?
Doesn't matter. Could be wrong. Okay. But the point is, now you're making me wonder. Shoot. Okay. Oh, 14/4. Now? 13/4.
Yeah.
Okay, that's what I meant to do. Now let's check it. 2 plus 3/2 is 7/2, right? And then 7/2 minus 1/4 is 13/4. Okay,
Yeah.
I think I did that right. Anyways, know how, if I gave you a calculator, you could figure out what all the terms of the sequence are, right?
Yes.
And you understand that this is a sequence. The point is, what does 1 over n converge to?
0.
0. What happens when I plug in 0 here? What do I get? 2. So I'm saying whatever this sequence is, it eventually gets closer and closer to 2. So I'm saying that the limit of this sequence is just going to be 2. That's what this proof is saying. The proof is saying the limit of the sequence you get when you plug in 1 over n is going to be exactly what you would have done if you would have just plugged in the limit of 1 over n into your polynomial.
No.
Yeah, we're saying that.
Oh, right, okay, right, yeah.
Okay. So that's what we're saying up here. The limit of plugging in our sequence b sub j into our nth degree polynomial is the same thing as just plugging b into our nth degree polynomial.
Are we going to be spending a lot of time in the future finding what a polynomial converges to? I assume that's where this is getting at.
Yeah, we're going to be taking polynomials and finding the limits as we approach points.
That makes sense. So this is kind of playing the groundwork.
Polynomials are combinations of polynomials. If you have a polynomial over polynomial, we call it a rational function, and we do a lot with rational functions. Okay, so we got, 1, let b sub j such that, let be a sequence such that its limit of b sub j is equal to b. Okay, 2. We're going to do this proof by induction, so base case. Let n equal 1. Then what do we get? Then the limit of p sub 1 of b sub j, a lot of notation here, so don't get lost in it, is equal to the limit of, what does a first degree polynomial look like? It's just going to look like that, right? We just plug this in for the x. You with me?
What's a first degree polynomial?
A first degree polynomial, so
And second degree and third degree.
p sub 0 of x, a 0th degree polynomial is just a sub 0, a constant. P sub 1 of x is equal to a sub 0 plus a sub 1 times x to the 1. First degree polynomial.
Is that, you want to use a again?
Second degree polynomial is equal to a sub 0 plus a sub 1 x to the 1 plus a sub 2 x to the 2.
Oh.
Where the a's are just any real numbers, doesn't matter. In general, an nth degree polynomial is equal to the sum from k equals 0 to n of things that look like this, where all those a's are just any real numbers you want. So just a times some real number times x to a natural number is what this is doing over and over again, where the natural number starts at 0, 1, 2, 3, all the way up to 10. So a first degree polynomial looks like this, but when you plug in b sub j to it, it looks like this. Right? So we're taking the limit of this thing. What is the limit of this thing?
Well, you can be,
What's the limit of a sub 0?
just a sub 0.
Just a sub 0. A sub 0 is a constant. Right? Maybe break this up into a couple steps. This is equal to the limit of a sub 0 plus the limit of a sub 1 times b sub j.
Okay.
Right? Just using the sum property on limits. Now a sub 0 is just a constant. So what's this sequence? If a sub 0 is 1, it's just 1, 1, 1, 1, 1, 1, 1, 1, 1.
So doesn't that look?
Its limit is just whatever the number is. It's just a constant sequence.
Oh, okay.
It's never changing. So this is just equal to a sub 0 plus b sub 1 times b. Oops. A sub 1 times b. The limit of a constant is just a constant. The limit of a constant times a sequence is just a constant times the limit of the sequence. And we already said that the limit of our sequence is b. Which is equal to p of b. P sub 1 of b. Right? So we just proved that for any first degree polynomial you choose,
How did that?
the limit of this polynomial of the sequence is the same thing as a polynomial of the limit of the sequence.
Oh.
Make sense? Maybe write this one more way to just bring it all the way home, which is the same thing as p of 1 of the limit of b sub j.
B sub 1.
B sub j. So the limit of p sub 1 of b sub j is the same thing as p of 1 of the limit of b sub j. So you can bring the limit inside the polynomial as one way to think about it. Make sense? Okay, so there's our base case.
How are we moving from the end of that first line to the beginning of the second one? So a sub 0 plus a1 times b is equal to b sub 1 of b.
I don't know
Because that's the
where you're
definition
talking.
of the polynomial.
How do we go from here to here?
No, later.
Here to here?
Right, no, I'm-
That one,
Here to here?
that one to
From
that one.
that to the next one.
From here to here?
Yeah. That's just
We went from here to here the exact same way that we went from here to here.
Oh,
This is what a first degree polynomial looks like. This is what a first degree polynomial looks like.
okay.
Right? Okay. So, 4. Assume for n equal to k that the limit of p sub k of b sub j is equal to p sub k of b. So assume that our statement's true for k, I need to show that implies it being true for k plus 1. You understand how you finish the proof now? Five. Then the limit of p sub k plus 1, a k plus 1 degree polynomial, of b sub j is equal to, let's write out what that polynomial is equal to. That's equal to the limit of the sum from k equals 0 to k plus 1. Uh-oh, we can't use k. Here, let me rewrite this line and lower it so I'm starting some room. Then the limit of p sub k plus 1, p sub k plus 1 of b sub j is just equal to the limit of the sum from, I don't know, I equals 0 to k plus 1 of a sub I times b sub j to the I. Don't get lost in the notation.
Don't we need to create a set? Say a equals the set of all things that make that equation true or something?
You can, but we're going to assume that you're okay. I showed that 1 would be in that A. I assume that k is in the A. Now I'm going to show that k plus 1 would be in the A. But
You're just not, okay, I mean,
put that aside for now. Make sure that you can follow what we have written here. the limit of a k plus 1 polynomial when you plug in b sub j to the polynomial is the exact same thing as the limit from I equals 0 to k plus 1 of a sub I times x to the I, but wait, we plugged in b sub j for x. You following all that dense notation? So now I'm going to pull out the kth plus 1 term. So this is equal to the limit of the sum from I equals 0 to k of a to the a sub I, b sub j to the I, plus a sub k plus 1 times b sub j to the k plus 1 and the limit. I just pulled out the k plus 1 term. And this is equal to the limit of a kth degree polynomial when you plug in b sub j plus b sub j to the k, oh, I forgot my a sub k plus 1, sorry, plus a sub k plus 1 times b sub j to the k plus 1. Right? This is a kth degree polynomial when you plug in b sub j. That's exactly what this is. This is equal to, use our sum property, the limit of p sub k of b sub j plus the limit of a sub k plus 1 times b sub j to the k plus 1. Right? And then we know what this is, which is equal to p sub k of b by assumption. We assume that for any kth degree polynomial, this limit is just equal to that. So this limit is just equal to that. Plus the limit of, well, I'll pull out my a sub k plus 1. This is just a constant, so I'm going to pull that out. A sub k plus 1 times the limit of b sub j to the k plus 1. Now, I'm going to make a little bit of a leap here and then justify it in a second with something I don't think is worth proving all the way because I think you'll immediately see it. P sub k plus a sub k plus 1 times b to the k plus 1. So I'm saying that the limit of b sub j to the k plus 1 is the same thing as b to the k plus 1. How do I justify that? I use the product property over and over again. Right? The limit of b sub j times b sub j to the k. Do you see how I use the product property for this over and over again? Let's just do some scratch work at the bottom. I won't do proof, but we'll just show it really quick, like this. The limit of, this is completely different from this. I'm just going to write some arbitrary sequence. A(n), we'll say to the third, is equal to, we know that this is the same thing as the limit of a(n) times a(n) squared is one way that we can think about it, right? Which then we can break this up into two products and take their limits individually. What's the limit of a(n)? That's just a times whatever the limit of this is, which is just a(n) times a(n). And then we just use the product property again. So we can use the product property over and over again, and ultimately we're going to get a cubed. Same thing. So we need to use the product property k times, and we're going to get b to the k plus 1. And you can do a quick proof by induction if you want, so that's the case for any natural number. But I don't think it's worth it. Okay. So then that's equal to that, but notice that that is exactly what P of k plus 1 of B is.
Yeah.
A kth degree polynomial plus a k plus 1 term is going to give me a k plus 1 polynomial. Right? Six. Therefore, it holds for all natural numbers n. Proof by induction, right? Any questions on that?
Take a picture of it really quick.
Can you take a picture of it?
Yeah.
Sure. I mean, you have it online. But this little proof right here is going to be something that we reference down the road a lot. The idea that the limit of a polynomial of a sequence is the same thing as a polynomial of the limit of the sequence, because it combines so many of these proof properties all into one.
Cool.
Okay,
Are we starting, have we started,
we just finished 2.1.
okay.
We haven't done anything past 2.1. Doing homework took most of our time. But 2.2 is relatively small. 2.3 not so much. So, I don't know, maybe I'll just talk high level about what 2.2 is, and then we'll come back next time and actually do 2.2. Make sense? So 2.2, we introduced the idea of a sequence being bounded. So a sequence is bounded if it always falls between the absolute, well, you already have intuition for what a sequence is bounded is, I think. A sequence is bounded means it doesn't go off towards infinity and it doesn't go off towards a negative infinity, right? So whatever the sequence is, so here's 0, here's our sequence. Whatever, if we plot all the points in the sequence, wherever they don't go off towards infinity, and they don't go off towards negative infinity. So another way to say it is I can find some lower bound, B, and some upper bound, A. So that they're always between those two numbers. Now the way that the book is going to say it is a sequence AN, so we're talking about AN here, we plotted all its points, are always between these two numbers. They're going to say that a sequence AN is bounded if it's less than or equal to the absolute value of m for some number m. What's the m in this case? I just look at whatever number has a bigger absolute value out of A and B. So let's say A is, give me some number.
80.
80. And B is, give me some number.
36.
Well, it's got to be negative,
Less than
so.
0, so -36.
Negative 36. You're making our picture look like it's like, we'll say it's negative 96. So, let's say I've got AN, and I know that it is always between 80 and negative 96. Therefore, it's always between the absolute value of whichever of these numbers is bigger, in this case, negative 96. So if I can find some number, in this case, negative 96, so that AN is always less than or equal to the absolute value of that number, then it's bounded. Now, I could have also used, if I knew that this was the case, I could have also used for m, 1000. There's no reason I need to find the smallest m and squish it as close as I can. Don't make it hard on yourself.
It just has to be 1.
You just have to be able to find a number such that the absolute value of the sequence is always less than or equal to the absolute value of that number. If you can find a number that makes that true, the sequence is bounded. It for sure doesn't go off towards positive infinity, and it for sure doesn't go off towards negative infinity. That's what we mean by bounded.
But at some point, will we be finding the upper and lower bounds of the sequence?
Well, we've already talked about upper bounds and lower bounds, and we've already talked about least upper bound and least lower bound. Now we're just talking about bounded, period.
Why?
How do you find?
Just because it's an easy property to reference. if I have a bounded sequence, then there's some things that are going to be true about it. I could say if a sequence is both bounded from above and bounded from below, and use the fact that we have those two definitions. But now I just have a definition for bounded. So now I can say if the sequence is bounded, and then we can start proving things that we know just because we know sequence is bounded. What?
How do you show that a number is not in sequence?
How do I show a number is not in AN?
Yeah. I feel like it's simple, but I'm not quite sure how to do that.
Well, AN, if you want to show something's not in it, you need a particular AN. So if I want to show, so if we're talking about AN is equal to 1 over N, then what do I want to show isn't in there? I know 2's not in there.
A bunch of things aren't in there.
Yeah, a bunch of things aren't in there. How do I
Okay,
know?
so you're not saying prove that there's something that's not in there. You're saying prove that it's bigger than the sequence.
Prove it's, so I claim 1 over N is bounded. How do I know? Because the absolute value of 1 over N is always less than or equal to the absolute value of 1,000. There, it's bounded. I also know it's bounded because I know that the absolute value of 1 over N is less than or equal to 1, or the absolute value of 1. Therefore, it's bounded. If I can find some number such that the absolute value of that number is always greater than or equal to the absolute value of the sequence is bounded.
But we're not going to be really specifying the number. It's more going to be
If I say,
X is
show that a particular sequence is bounded, you just find a number.
okay.
If you're just using the fact that a sequence is bounded, then you know that if I have a sequence An, then there must exist some m, I don't know what it is, but some m such that this is always true
Okay.
for any natural number n, for any point in the sequence.
So do you want us to do 2.2 homework?
You can start trying it if you want, and that way if you have questions that you feel like I don't answer in class,
Okay.
you can ask me questions about it. A set S contains AN if for each index n, AN is in S. That makes pretty intuitive sense. How do I know that a sequence is in a set? I don't know how to write a set without writing a sequence. So here's a sequence, and I want to say, is the sequence, is it in the rationals? Yes, because every number in there is a rational. Therefore, that sequence is in the rationals. So that's what we mean when a sequence is in a set. If every element of the sequence is in the set, then the sequence is in the set.
Wow.
You almost want to say that this is just a subset of this,
Yeah.
but remember that sequences also keep track of order, so they're not necessarily sets. But if you took the set of all right-hand elements in the sequence, and it's a subset of the set, then yes, that's what we're talking about. But remember, we have this ugly notation where we're tricking you into thinking we're talking about a set when we're not really talking about a set. And in topology, it's going to be even worse because we're going to do sequences like this.
Why?
Ooh.
Because that's how that author does it.
Why is it not a standard? Like, this is what everyone should do because it makes no confusion.
What's math about?
So I think if you're in a class where you don't have to deal with sets directly a lot, then the authors will use this kind of notation. But topology, since we're always talking about sets, it's less confusing to do this.
What about this class? We're using sets all the time.
Not directly. In topology, you're always dealing with sets directly themselves. In this class, we're dealing with really high-level things. I mean, we're dealing with sets that also have other structures. We're very rarely just talking about a raw set. Anyways, so let's see. We're going to prove that a set S is dense in R if every number X is the limit of some sequence in S. Oh, that's going to be a fun one. Should we try and get some intuition for what that is? Let's write out what exactly that says and try and get some high level intuition. A set S is dense in R if and only if for all x in S, comma, there exists some sequence an in S such that the limit of an is equal to x. So a set S is dense in R if and only if for every point in the set I can always find a sequence in the set that converges to that point. Then the set is dense in R. Let's look at a set really quick that's not dense in R. Now,
Integers.
no, the set of integers, I feel like I'm missing something here. Because why can't I just use the number itself over and over again? If every number x is the limit of some sequence in S, set S is dense in R if and only if for every point in the sequence, or in the set, there exists a sequence in S such that the limit of that sequence is equal to x. I'm wanting to say that for some reason that sequence can't just be x, 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 x. Because we know that, for example, this is not dense in R, right?
Mm-hmm.
Which means that I should not be able to find, which means that this shouldn't hold. Which means for every point in here, I should not be able to find a sequence that converges to that point.
Mm-hmm.
But if you pick one, I can pick the sequence 1, 1, 1, 1, 1, 1, 1, 1. If you pick two, I can pick the sequence 2, 2, 2, 2, 2, 2, 2, 2, 2. So, good thing we went over this because I'm going to need to go back and reread from the book because I feel like I'm missing something on my paper. Oh well, we'll call it there. So you can use the rest of class to start working on homework. You can ask me any questions you want, and otherwise I'm going to start reading the book and